All right. So it is 3:30. We can go ahead and get started. Yeah, how's everyone doing? Is everybody excited about the end of the semester? Hor- Horrendously. Oh my goodness. Hopefully everything is not horrible. But yeah, I don't know about you guys. I'm definitely looking forward to the end of the semester. Um, So yeah, I think just in terms of housekeeping, I think we're good to go on the project. So do make sure you're finding, getting set up with a group relatively soon. I'm forgetting when I set that deadline for. I think it's coming up pretty soon. And again, if you're having issues, finding group mates to work with, definitely reach out to me or reach out to Jordan. We can help, set you up with a group. And the bullet point is you definitely, given how many people we have in the class and how many presentation slots we have available, unfortunately, it's again not feasible for everybody to work by themselves or work in a group with less than 3 people. And furthermore, it is quite a lot of work. So you want to make sure you're not unnecessarily burdening yourself with like an excessive amount of work, basically. But yeah, do make sure that you're going through that practice test as well, especially as we're moving on to some of this newer content. So we do have 3 more units that we're going to be getting through by the end of next week, God willing. So we're going to finish up with Birch clustering today, hopefully. And then we're going to move on to another online clustering algorithm, which we call mini batch k-means today. And then the final clustering algorithm that we're going to talk about next week is spectral clustering. So just wanted to we should be moving on to the application of Birch today. So just as a reminder, Birch is our first online big data clustering algorithm that we have introduced in the course. And so, one of the key benefits that we discussed that Birch can essentially provide to us is that it's actually this really cool memory efficient clustering algorithm that does not actually require you to have the entire data set that you'd like to cluster loaded in your computational working environment at any one given point in time. Now, we basically, under a scenario such as that, we, we did discuss potential workarounds, right? So, for instance, one hack, I guess you could say, that we could try in certain scenarios is we can, for instance, take a sample of the data set that we'd like to, cluster overall. So let's just say, for instance, we were able to get by with, loading a tenth of the entire data set into our Jupyter notebook. And so what we might try to do is cluster that 1/10 of our data set using, one of the clustering algorithms that we know, like k-means. And, what we could do is, keep those centroids around and then basically one at a time load in the remaining, like, let's just say, the remaining 9 batches of data that could theoretically fit into our Jupyter notebook. And then one at a time, assign each of those remaining observations to the closest existing centroid. Now, basically, what we discuss is that we might actually expect to have good performance using a technique such as this if we could assume that our first batch that we used to initially cluster the data was fairly representative of all subsequent batches that we, read in or we fed in and, assigned to their closest centroid. However, if the initial data set that we use to cluster the data set or cluster, find our centroids was not representative of the full data set, then what we discuss is that we may actually not expect necessarily to get very good performance using this technique. And so one of the benefits, as we're seeing here with Birch, is that it is actually going to be this really cool technique that allows for us to iteratively feed in observations into what we called our CF tree, our clustering feature tree. And in so doing, it allows for us to iteratively update this tree, which essentially is storing the nature of the clustering structure without actually needing to have the entire data set in any given one iteration. And then the beneficial thing that we're going to see here is that, you know, even if our first few batches or observations that we fed into our birch tree are not representative of the full data set, then this is actually okay. So what we're going to see is that the birch clustering algorithm actually has ways for your tree to essentially course correct, to allow for modifications in the existing detected clustering structure to basically incorporate new batches that might, for instance, start showing the presence of new clusters that your previous batches may not have necessarily picked up on. So we're going to basically we're going to take a data set and we're going to essentially evaluate how well each of these two clustering techniques did when it came to actually identifying the clusters in the data set here. So before we do that, we'll actually get through how the overall birch clustering algorithm works. And so you want to remember there's actually 4 phases of the birch clustering algorithm. So on Tuesday, we were simply just discussing how phase 1 works. And so the overall goal of phase 1 of the birch clustering algorithm is to simply just feed in each of our observations and build our CF tree. So basically build our CF tree, which is going to iteratively detect and update its notion of what the clustering structure is based on the data sets or based on the observations that have been fed into the tree so far. So there's a complicated set of steps that we go through when it comes to actually building that tree. So essentially, what we're going through here is just 5 iterations of us iteratively incorporating 5 observations into this tree. So this is where we left off in iteration 3. So we had incorporated 2 observations into the tree so far. And at the moment, our tree is not very, it's not very large. It's simply just comprised of a single root node, which is also the leaf node because it's at the bottom. So next iteration is we'd like to incorporate object 5.5 into the tree. So as we saw, when we incorporate any given new object or observation into the tree, what we temporarily assume is that it is just a singleton cluster. So we subsequently represent the CF, the clustering feature of this cluster, comprised of just 5.5. So again, this would be a cluster comprised of one observation. The linear sum of the observations in this cluster is simply just the point itself, and the squared sum of the observations in this cluster is simply just the squared of the point itself. Okay, and so the centroid of this incoming subcluster is simply just the point itself. Okay. And what we know at the moment is that there are 2 subclusters represented in the root node or the only leaf node of our tree. So when it comes to figuring out what to do with an incoming subcluster, we go through step 1. So step 1 is about choosing the closest leaf node. So at the moment, there's only one leaf node, so we simply just choose the one leaf node. So once we've chosen our leaf node, we then go about modifying that leaf node. So in our chosen leaf node, what we do next is we find the closest entry in this leaf to the incoming subcluster. So for instance, we can see that this centroid is closest to this centroid. So we temporarily assign this incoming subcluster to this leaf node subcluster. And then we ask ourselves, are we allowed to merge these 2 subclusters? So unfortunately, I don't know if I want to say unfortunately, but the answer is no, right? So you want to remember that we stipulated that any leaf node subcluster is not allowed to go over our pre-specified diameter threshold of 3. So basically this would lead to a overall pairwise distance larger than 3. So basically the answer is we cannot merge these 2 subclusters. So someone's asking, where did you get 1 and 169? So this is 14 squared. So this is 1 squared and this is 14 squared. Okay. So if we can't merge our incoming subcluster to our closest selected subcluster in the leaf node, then the next question we ask is, well, okay, can we simply just add this? We add that subcluster CF as an additional entry in the leaf node. Oh, sorry. Yeah, you're right. Okay, yeah, it should be 196. Thank you. A temporary moment of dyslexia there. Yes, 196. Okay. And so, unfortunately, right, because we said that our leaf nodes are only allowed to contain at most 2 entries, the answer to this question is also no. So if both of these answers are no, what it means is that we need to split the current leaf node that we're considering. And so this is how we go about splitting a leaf node. So basically, when we split a leaf node, we consider all of the current subclusters represented in that leaf node and the incoming subcluster. And then what we do is we pick out the 2 furthest away subclusters. In other words, we pick out the 2 centroids, which are the furthest apart from each other. So that would be this subcluster and this subcluster. And so what we do is we would seed 2 leaf nodes with those 2 furthest apart subclusters, right? And then we take all remaining subclusters and we assign them to their closest seed subcluster. Basically, we assign it to the subcluster whose centroid is closest to their centroid. Okay? So we see that our incoming centroid, or excuse me, our incoming subcluster, which is comprised of simply just 5, 5, is assigned to the leaf node that has this subcluster here. Okay? However, what we've done now is we've split our leaf node into 2. And so basically our CF tree has the property that no 2 nodes are not allowed to have a connecting parent node. So what that means is that we would need to modify the path to the leaf. So therefore, what we would do is we would need to create a root node or a parent node above these 2 now leaf clusters, or leaf nodes, excuse me. And the way that we would go about updating that parent node would be to basically represent in the 2 entries of this parent node the 2 clusters that we would get if we had merged each of the subclusters that exist in that given leaf node. So in other words, what we're doing here in this entry is we're representing the cluster that we would get if we merge these subclusters, or the cluster that we would get if we merged these 2 little green subclusters. And so we would want to represent the CF, or the CF entry of this cluster of subclusters. And we discussed the CF entry has this very nice property in that, if you want to represent the CF of a cluster, or basically a CF of 2 or however many merged subclusters, all you need to do is simply just add the corresponding CF entries together. So we can see that now this cluster of subclusters is now comprised of 2 observations. The linear sum of all of the observations represented in these 2 subclusters is simply just 6, 6. And similarly, the squared sum of all of the observations represented in these 2 subclusters is 26, 26. And so basically, with just this CF entry, you have everything that you need essentially to calculate all the important pieces of that represented cluster. You can use this, for instance, to calculate the centroid, right? So just take 6, 6, divide it by 2. And similarly, you can also use a little bit of algebra to calculate the diameter of this cluster as well as the radius, if that's what you're using. So basically that's how we would update this CF entry. And then similarly, we would want to create a CF entry that corresponds to this leaf node. However, there's only one, subcluster represented in this leaf node. So basically, we simply just rewrite that one subcluster's CF entry here. Okay. So therefore, this would be our current tree, which we've now updated. All right. Questions on that? All right. So next iteration. It's getting a little bit more complicated now. We want to incorporate the next observation in the full data set, which is the 0.22. So what we do again is we convert that incoming point into its own singleton subcluster, which has a centroid of 2,2. Okay. And so the next step when it comes to incorporating this new incoming subcluster is we need to find the closest leaf node. Okay. Now in this case, what we're going to do is we're going to compare this centroid to these two centroids in the root node. And we're going to find basically which of these two cluster centroids is this centroid closest to. You can see that 2,2 is closest to 3,3. Basically, it's like these two centroids here. It's kind of hard to show. And so what we do, because we selected this particular leaf node's centroid, we follow that leaf node. We go down the tree to the corresponding node or child node that we have selected. So we selected child node 2, so we move down the tree to this node. Now, basically, if this was not a leaf node, we would basically go through the same process. We would again take a look at which of these two centroids is this centroid closest to. However, because we've made it to the leaf node, we've basically completed step 1. However, in step 2, the next question is basically, which of these two leaf node subclusters is this incoming subcluster closest to? And so you can see that the centroid 2,2 is closest to the centroid 1,1. So we would assign it temporarily to this corresponding subcluster. And so the next question is, are we allowed to merge these two subclusters? Am I allowed to merge this incoming subcluster with this subcluster? So now in this case, the answer is yes, right? Because if I were to merge these two subclusters together, then their resulting diameter would not go over the threshold of 2. Or in other words, the average pairwise distance of all points in these two subclusters would not go over 2. So therefore, we are allowed to merge these two subclusters. However, we're not done. We need to then modify the path. So, all right, 1 second here. Feel this in just 1 second. So what changed in this CF tree is basically these two observations joined together in the same subcluster. So therefore, we needed to represent that in the corresponding CF entry. So basically what we had to do first was take this CF entry and add it with this CF entry to represent the cluster that would form when we merged these 2 points together. So we would get this updated CF entry that corresponds to this cluster here. However, what that means is that now this leaf node has been modified. So therefore, we need to update the corresponding entry in, or basically the corresponding entry of the parent node that, or the parent node of this particular leaf node. So we would need to update this entry here. So therefore, what we would need to update or do is, merge or add these 2 CF entries together to get this, to basically represent the new resulting, or to represent the CF entry of this new resulting sub or cluster that you would get if you had basically joined these 2 subclusters together like that. Okay. Questions on that? Okay. All right, so it's getting a little bit more complicated. And so the final, because we're only assuming we have 5 observations in our data set, the final iteration is one in which we would like to incorporate the observation from our data set 15.5. And so again, we represent this new observation as its own singleton subcluster. So we give it its corresponding CF entry. Okay. And next, what we want to do is we want to find the closest leaf node to this incoming subcluster. So we would evaluate which of the root nodes centroids or cluster centroids are closest to the centroid of this incoming subcluster. Okay, and so we can see that this centroid here is closest, it's closer to this cluster's centroid than it is to this cluster centroid. So we would assign it first to this entry in the root node. So basically, we would assign it first to node 2. So we would go down the tree to node 2. Okay, and so it just so happens that node 2 is the leaf node. So we have, in fact, now found the closest leaf. Okay, and then the next step. So once we found the closest leaf, we look for the closest subcluster in that leaf node. So in other words, we would find the centroid represented in the leaf node that is closest to the incoming subcluster's centroid. So we can see that this incoming subcluster centroid is closest to this subcluster's centroid here. And so you next ask the question, are we allowed to merge these 2 subclusters? Okay, and so the answer to that is no, because the resulting cluster that you would get would have a diameter that is greater than our threshold of 3. Okay, and so our next question is, well, okay, can we add this CF entry as another entry into this leaf node? And the answer to that is also no, because that would put us over our maximum CF entry limit of 2. So because we can't do either of those 2 things, we need to take this leaf node here and split it into 2. Okay, and so we use the same procedure that we used in the previous step, right? So basically, we find the two furthest apart subclusters that we are considering. So basically, out of all the subclusters in this leaf node and this incoming subcluster, we find the ones that are the furthest apart. And so we end up seeing, oops, that's the wrong one. We end up seeing that these two subclusters are the furthest apart. So therefore, those two subclusters are selected as the seeds for our two new leaf nodes, which are a result of the splitting of this leaf node. And then we basically take all remaining subclusters and assign them to their closest seed subcluster. So basically this subcluster here would be assigned with this seed subcluster here. Okay. And so now we have, the situation in which we actually have three, so what we would do technically is, okay, well, now we have these three leaf nodes. And so what we theoretically would do next is we would update the tree in which we would create a corresponding CF entry that corresponded to the cluster that we would have got if we had combined each of the subclusters represented in the leaf node. So basically the cluster of all these subclusters, the cluster of all these subclusters, and the cluster of all these subclusters. But we run into a problem here. So what's the problem with this CF tree? So does this violate one of our constraints? Yeah, exactly. So we also stipulated that our non-leaf nodes are also not allowed to have more than two entries. So therefore, because of that, basically if the creation of leaf node entries results in a non-leaf node entry a non-leaf node with too many entries, then what we need to do is take this non-leaf node and also split it into two. And the way that we split it into two is by using the same procedure. So basically, we find the two furthest apart centroids and we use those as seeds for our two nodes that we are now creating. And then we basically assign all remaining clusters to their closest seed cluster centroid, essentially. Okay, so the two furthest apart clusters are in fact going to be the ones with centroid 15.5 and centroid 2.67, and then we end up assigning the remaining cluster with centroid 114 to its closest seed cluster, as we did here. Okay. However, now we've essentially created, basically our root node has been split into two. And so we have this rule that says we can't not have a single root node. So basically every two or however many children need to have a parent node. So what we need to do is increase the height of our tree, creating a new root node, which represents the cluster or the set of clusters that we were to get if we had combined each of the clusters represented in these two nodes here. So basically this entry here in our new root node corresponds to node 3, or in other words, it is the cluster that we were to get if we were to combine each of the clusters represented in this node. And then this new root CF entry here represents or corresponds to child node 5. And it represents the cluster that we would get if we were to combine all of the clusters in this node. However, given that there's only one cluster in this node, we simply just rewrite that cluster's information here. Okay. So basically, that is, in this very small toy example case, there was only 5 observations that we wanted to incorporate into the CF tree. And so therefore we have created our CF tree, which essentially contains information about the clustering structure of this data set. So take note, our final CF tree has now represented 4 subclusters of the data. However, take note though, we don't actually know at the moment which cluster each of those 5 observations should belong to. But what we do know is that there exists, based on all the data that we fed in, there exist these 4 subclusters, which have each of these 4 corresponding centroids. Okay, so phase 1, we've built our CF tree, which in the case of very large data sets, very efficiently represents the clustering structure. Now, you might note here that it's like, well, okay, we only had 5 observations in this data set, and we have this tree with like, 3 layers to it. So in real, scenarios in which you have, really large data sets, this tree actually, does become more, memory efficient, if you will. However, there's one final step that we actually need to, talk about and go through in phase 1 of the Birch clustering algorithm. And basically this step 4 of phase 1 is meant to be activated anytime there is a leaf split. So basically, if you have split a leaf in steps 1 through steps 3, what this step 4 essentially allows for the tree to do is it gives it the opportunity to course correct if it starts to get information that perhaps a better clustering structure might be better to use essentially in the presence of unrepresentative data sets. So in other words, like if you start to feed in observations that are exhibiting, some clustering structure which we have not yet detected, basically step 4 allows for us to basically course correct and start, allowing for the presence of new clustering structures to essentially be detected. So here's how the step 4 works if it's activated. So basically, if you split a leaf in one of the subsequent steps for your given iteration, then what you do is you move up the tree and then you find the first entry or the first node in the tree that actually did not require to be split. So therefore, it just so happened in step or iteration 5, we saw this, this leaf here did in fact, this leaf node here did in fact need to be split. So therefore, that led to actually this non-leaf node, needing to be split as well. So you might say that the first node that did not require, splitting, if you will, was actually this new root node that we had created here. So in theory, what you would do, given that we had split, one of these leaf nodes, you would select this root node here to, basically allow for a little bit of clustering structure massaging, if you will. And so what you would do is you would find the two closest entries in this node that you have selected. So basically the first node to not be split. Okay, so that would simply just be, the only two entries that we have in this root node. And then you would ask the question, did these two entries involve the split? So in our case, the answer is yes, right? Because basically these two nodes actually were split. And that's what led to the creation of, these two entries in this, root node here. So in our case, the answer is yes. So basically, if the answer is yes, then, you basically don't do anything. Step 4 is not activated. However, if it was the case that these two closest cluster entries basically did not involve the split, then basically what step 4 allows for you to do is see if merging these two close clusters might actually be a good idea. Or basically it allows for you to merge these two close clusters together. So what you would theoretically try to do is you would try to merge these two clusters here. Now the thing here is if you merged these two clusters, then what that would do is it would merge all of the child node clusters together, all in the same child node, okay? But that's going to lead to a problem, right? Because then you would have a corresponding child node with 3 entries in it. So basically that would put you over the limit for one of the child nodes. So in a situation like that, what you would do is you would select the 2 furthest away clusters represented in those 2 leaf nodes that you were trying to merge, and then basically use those as cluster seeds to rearrange all of the clusters that existed. So basically, let's just say these. Let's say these were the 2 furthest apart clusters here. So basically you would choose this as a seed, choose this as a seed, and then you would actually assign this cluster to this cluster here because they were the closest. Okay. And so it's kind of, if an event, like if you're using this reseeding process and, one, like let's just say one of your leaf node entries ended up going over the maximum, if you will, then basically what the algorithm says to do is just like take some of the leftovers or take some of the excess clusters and basically just put it with the other cluster essentially. So the purpose of this potential step 4 merging step is to allow for the algorithm to see if there might actually be some subclusters or some clusters that should actually be lumped together, because we're finding more of a separation amongst some of the incoming sets of observations that are being fed into the algorithm. So yeah, so the bullet point is step 4 allows for Birch to recognize new clustering or new clusters in newer batches of data that may not have been observed in the first or in the initial observations, which had been read into the tree first. Okay. All right. So that's basically phase 1 of Birch. So any questions on that? Okay. So I mentioned, there's actually phase 2 and phase 3 and phase 4 of Birch. And there's also actually a extended version of phase 1 if you wanted to be mindful, if you wanted to allow for your Birch clustering algorithm to iteratively adapt to the size constraints or the amount of memory constraints that your computer has. So this is the extended version of phase 1 that you could incorporate if you wanted to, if you're actually implementing this, for real, like if you're actually implementing this without the help of scikit-learn. So for instance, you would start with an initial diameter threshold parameter t. And what we're going to discuss in just a second is that it's a good idea to start low. It's a good idea to start being very restrictive about how big your subclusters in the leaf nodes are allowed to be. So whatever your initial t value is, you start with that. And then in this extended version of phase 1, you start building your tree. Okay. Now let's just say, you've read in like 5 observations and you've got to this point where you're like, uh-oh, okay, my computer does not have room for a tree that has 3 layers. So let's just say that, it's too much for your computational memory constraints. So if you run into a scenario like that, you run out of memory, then what the extended version of phase 1 does is it stops the algorithm. It increases that subcluster diameter threshold t based on some step size that you pre-select. So let's just say it used to be the case that this was too large, but now maybe you might say, okay, well actually let's allow for a diameter threshold that incorporates all these together. So you increase that t, and then basically you rerun the algorithm again, not necessarily from scratch, but what you do is, so you're not basically wasting time in rerunning the whole algorithm. Instead, what you do is you take each of the leaf node CF entries that you had previously created, and then you start building your CF tree again, but rather than feeding in each of your individual observations as singleton subclusters, instead you feed in the existing subcluster CF entries that you had already created one at a time instead. So, if you had already clustered a lot of observations, so like let's just say this was like 1,000 here, then this actually saves a lot of time. So you're not basically refeeding the same information in again. So yeah, so you've increased your t, your diameter threshold, you start reading in these existing CF entries again, and you see how things go. So if you run out of memory again, then you basically go back and repeat the same process. You increase your t threshold even larger, reseed your or basically start building your CF tree with your new potential leaf node CF entries, and you keep going again. And so basically the extended phase 1 also has these other subroutines where it's like, if it detects that, perhaps one of these subclusters or a few of these subclusters are outliers, you have the option to essentially write information about those outliers to, some other location, if you will. So like you can kind of write it to some out of disk, some other location basically. So you're not actually storing all of these potentially superfluous information about outliers, in your Jupyter Notebook, working environment. And so basically, and eventually, like you will be able to create some tree that does not run out of memory. And so basically, once you've created your tree, you can reabsorb those outliers, back into your tree, if you will. But yeah, so basically the extended version allows for you to, build your tree while not running out of memory. Yeah. So pretty cool. Any questions on that? So basically, if you're using this extended phase one version, you want to be very careful about how you're selecting that initial diameter or radius threshold T. So for instance, let's take a look at simply just this data set here. So what do we think our CF tree would look like in this example if we were to set our diameter threshold to be 100? So if we set that T to be too large, what kind of tree would we expect to see here? Yeah, exactly. So we have made our cluster requirements way too loose. So what that means is that, as we fed in every new subcluster into our CF tree, we'd always assign it to the, one existing, leaf node cluster that exists in when we asked ourselves, am I allowed to merge those two subclusters? The answer would always be yes, right? Because we would not be going above our diameter threshold. So these two subclusters would merge. These two subclusters would merge. So eventually, you would end up getting just a single leaf and root node that was comprised of all 5 observations, comprised of the linear sum of all 5 observations, and the squared sum of all 5 observations. So in other words, your CF tree would actually pick up on no clustering structure at all. It would simply just cluster every single observation together, all in the same big cluster. So the thing here is if you set your T too high, in extended phase one, then your birch tree, so the bullet point is if you set it too high in your extended phase one initially, then the thing here is that the T is never allowed to decrease. Okay, so the extended phase one only allows for you to iteratively increase the T. So because of that, your tree may not detect the full clustering structure. It may, place some of the inherent clusters together. It may place all observations in one large cluster. Okay. In other words, our clustering result was pretty useless. We didn't really detect anything. On the other hand, though, let's think about what would our CF tree look like in this example if we were to set the diameter threshold to be 0.01. Okay, so all observations, yeah, would be leaf nodes. Yeah, so no merging would happen at all. So basically, because we've made our diameter threshold too small, basically what that means is that no observations or no subclusters when they're fed into the tree would be allowed to merge with any other existing subclusters. So we would have a CF tree in which all leaf node subclusters were singleton clusters. Okay. The problem is if you set your T too low in extended phase one initially, Actually, so I'll say if you set your T low in extended phase one initially, here's what might happen. What might happen is your basically all of your observations could be represented as singleton clusters and leaf nodes. All right, so that's going to end up taking up a lot of space. Your CF tree is going to dramatically increase in height very quickly. And so what might happen is that your CF tree might get too tall and you might run out of memory. However, if you're using the extended phase one, this is okay. So extended phase one will increase T iteratively. But because of this, because the extended phase one always allows for you to iteratively increase T if you run out of memory, it's a good idea to basically, because the algorithm allows you to increase T, it's a good idea to start small, or start with a small value of T as opposed to a larger value. Okay. All right. So that's extended phase one. Questions on that? All right. So the final three phases are actually not as complicated. So bullet point is phase one, regardless of whether you're using the extended phase one or just the regular phase one, the main point of it is to build your CF tree, which is trying to detect the clustering structure of your entire data set of observations that you have fed into it. However, the thing here is that because this CF tree is iteratively adapting as you read in more observations, it could be the case that observations which you had previously assigned to one cluster may actually be more well suited to another cluster, which may have formed as you read in more information. So basically, after even though you've created a CF tree, which represents the clustering structure of your data, if you've only done phase one, you have actually yet to cluster the actual observations in your data set, or you've actually yet to assign a formal cluster label to every observation in your data set. So therefore, phase four, i.e. the final phase, actually requires you to read in each of your observations again, cross-reference it with information from the tree, and then actually assign a cluster label. However, one of the potential downsides of simply just using your CF tree by itself to detect the clustering structure is that your subclusters that you end up finding in your leaf nodes tend to be a little bit too small, if you will. So for instance, you might have a scenario like this where, all the purple points are your actual data set observations that you have fed into the tree. But then all of these black points represent the centroid of each of the leaf node subclusters, right? So basically, like, this would have been a subcluster, this would have been a subcluster, so on and so forth. So we can see that, in a scenario such as this, the clustering represented by the leaf nodes, well, it was picking up on a local structure, right? It was picking up on, these observations should, generally speaking, belong to each other, or belong with each other in the same cluster. But it tended to be a little bit overzealous at the same time with respect to global structure. So, if we simply just assigned each observation to its closest leaf node subcluster, then, unfortunately, our clustering algorithm would be, unable to pick up on the global clustering structure, which might have existed like this. So therefore, we incorporate phase 2 and phase 3 to basically allow us to essentially, pick up more on this global clustering structure. So phase 2, what it does essentially is it, allows for you to potentially remove leaf node subclusters that might be like outliers, if you will. So for instance, like if the centroid of one of these leaf node subclusters is very far apart from the centroid of any other leaf node cluster, we can, you might decide to get rid of those particular entries in the leaf node or in the leaf nodes of your CF tree. So basically, phase 2 is simply just getting rid of outliers if that's what you want to do. And then phase 3, I think, is the more important part. So it's basically what it's doing is it's applying another clustering algorithm, not to the observations themselves, but to the centroids of each of the leaf node subclusters in your tree. So basically, if these are all your leaf node subclusters, what we do in phase 3 is we cluster those centroids into however many clusters that we want to help us detect that global clustering structure. So for instance, scikit-learn uses hierarchical agglomerative clustering with Ward's linkage to cluster your leaf node subcluster centroids. So what we'll do is we'll use single linkage out of ease, I guess you could say. So if we wanted to, for instance, so let's just say we wanted to actually, cluster this data set here into 3 clusters. Here's how we would use phase 3 to go about doing that. So we have 4 centroids corresponding to 4 subclusters on our leaf nodes. Okay. And these are these 4 centroids here. And so if we were using single linkage, for instance, to cluster these 4 centroids, we can see that 2 and 3. So basically, this is a cluster, this is a cluster, and this is a cluster. So again, with hierarchical agglomerative clustering, all observations, or centroids in our case, start off as singleton clusters. So centroid 2 and centroid 3 are closest to each other, so they would merge first at some proximity level. Okay. And looks like centroid 1 and this cluster are closest to each other because these 2 observations are considered closest. So basically, these 2 centroids, or excuse me, these 2 clusters would merge next. Okay. And then finally, these 2 clusters of centroids would merge last with a proximity that is basically this distance here, i.e. the distance between the 2 closest observations, or centroids in our case. So these would merge last. Okay. Proximity would be our single linkage proximity, i.e. the distance between the 2 closest points. Okay. And so, for instance, let's just say that we wanted to, we had an idea that there was a overall global clustering structure with 3 clusters. So based on that, we could extract the clustering. Oops, not that one. We can extract the clustering with 3 centroid clusters from our dendrogram. So this here. And then what we would do is, well, okay, so this creates one cluster. This creates another cluster, and this creates another cluster. This gives us centroid cluster 1. Give me centroid cluster 2. And this gives me centroid cluster 3. Right. Basically, this is a cluster with simply just this centroid. This is a cluster comprised of these two centroids. And this is a cluster comprised of this centroid. And then in order to move on to phase 4, in which we actually cluster not the centroids, but the original observations themselves, what we actually need to do is calculate the centroid of each of these centroid clusters, right? So basically I would calculate the average of these 2 points, calculate the average of simply just this point itself, and calculate the average of simply just this point itself. So this would be, so just give me a new centroid cluster centroid, 1 of simply just 15, 5. So give me a new centroid cluster centroid. Basically the average of these 2 points, which is 3.25 and 3.25. This is my new centroid cluster centroid, which is simply just this centroid itself. Oh, my bad. This should be 1 and 14. No, wait. This one should be 15, 5. Okay. Yeah. Okay. So what we've done is we've created now 4 centroids of the clusters of centroids. And so we actually want to cluster the actual observations from our original data set. What we would need to do in phase 4 is re-feed each of our observations back, or basically reload each of our observations back into like our Jupyter notebook or whatever, and assign each of those observations to their closest centroid cluster centroid as follows. So that would give us the actual corresponding cluster labels. Okay. So that is all of the many phases of the Birch clustering algorithm. Yeah, it's definitely one of the longest algorithms to explain. But yeah, any questions on that? Okay. So yeah, it's, one of the downsides is that, it does, it's not one of the most explainable clustering algorithms. But as we're going to see, it does allow for us to, very efficiently build this, memory efficient object, which stores all of the information about the clustering structure that we might need. And so the runtime of this algorithm is actually linear, which is really cool. So it makes it very scalable. It does tend to give you very high quality clustering structures detected, even just in the first scan. A couple other things. Oh, another cool benefit of Birch is that it's actually very easy to parallelize. So for instance, what you can do is you can actually have multiple computers basically building their own distinct CF trees based on a subset of observations from your data set in parallel. And then basically, let's just say you have, 10 computers who've built two CF trees based on 10% of the, or 10% of the data. And so what you can do is, once you've built those 10 CF trees, you can take each of the leaf node CF entries for each of your trees, refeed those into a single CF tree, which is essentially designed to combine the information from each of those 10 CF trees that you've built. So pretty cool stuff. A couple other things. Yeah, and so a lot of the other benefits we've sort of already discussed quite extensively. So cool thing about this is you don't actually need to have, you don't actually need to load the full data set into your Jupyter Notebook working environment. At any one given point in time, to actually run the algorithm. It allows for you to iteratively update the algorithm as, or the clustering structure as new observations come in. And furthermore, as we're going to see, it's even effective when your initial observations that you've read into the tree are not necessarily representative of the full data set. And this is where step 4 of phase 1 really comes in handy. However, one of the downsides is, as we're seeing here, like we're using a lot of the same metrics that clustering algorithms such as k-means end up using for measuring cohesion and measuring separation. So because of that, Birch tends to be most effective when it comes to clustering data sets that are, some of the same types of data sets that that are most effectively designed, are best used when you're using k-means. So for instance, like, data sets that don't have a lot of noise and outliers. And when you have clusters in which they are, spherical, equal sparsities, the same number of observations in them. Okay, when you know k ahead of time, clusters. Okay, so basically, same types of data sets that k-means is ideally designed for. So in other words, it's not as good at detecting the clustering structure in data sets that don't meet the specifications, these ideal properties. Okay. All right. Any questions on that before we move on to the application? Okay. All right, so very quickly, we are going to use, I guess you could call this a clustering benchmarking technique. The key thing here that you want to remember is that clustering is a unsupervised learning algorithm. So the main idea behind that is that we don't ever have, it's not usually assumed that we ever have like an answer key for really determining how well our clustering algorithm did. Or in other words, we aren't often supplied with a pre-selected response variable in which we can say, okay, I see that my clustering algorithm put this observation with this cluster label, so you basically you don't really have a set of answer keys for evaluating how well a given clustering algorithm did in practice. Now the thing here is oftentimes when we are trying out or when we're designing a new clustering algorithm, we do use benchmark data sets in which we sometimes assume that there is a correct answer. And what this can essentially allow us to do is get a sense as to how well a clustering algorithm might perform under a given set of clusters in which we believe that there is potentially a right answer. So to test the performance of the Birch clustering algorithm in comparison to this partial k-means clustering technique, which we discussed, we're going to use this benchmark data set here. So basically, this data set here is comprised of randomly generated data from 8 highly overlapping Gaussian distributions. And so basically, if we wanted to, we could consider the particular Gaussian distribution that a observation was drawn from. We could think of that technically as the right answer, or in other words, the cluster that a particular observation should be assigned to in a given clustering algorithm. So what we're going to do is we're going to, as a benchmark evaluation, we're first going to evaluate, well, how well k-means might do when clustering this full data set here. And so the thing here is, let's just say we were to apply k-means to this full data set, and we were to compare the k-means cluster labels that we were to get to the Gaussian labels, or in other words, the label of the Gaussian distribution that observation was drawn from. So would we expect to see this perfect correspondence between our k-means cluster labels and our Gaussian labels? Or are we kind of setting ourselves up for failure by expecting that? Or in other words, maybe if we were to calculate the adjusted RAND score between our k-means cluster labels and our Gaussian labels, is it fair to expect that we get an adjusted RAND score of 1? Yeah. So no, it's not quite fair. The reason why is, take a look at how highly overlapping these Gaussian distributions are, right? So, if I was running k-means, the ideal scenario, right, would be to take this, this observation here and assign it to this blue cluster, right? Because it's closest to that blue cluster centroid. But we can see that, at the very least for this observation, it actually belongs to this Gaussian here. So because these clusters are so highly overlapping, it would be very unfair or unrealistic of us to expect that even with the best clustering algorithm, we would, it'd be very unfair to expect that we're going to get this perfect one-to-one correspondence between the Gaussian label and our cluster labels. However, we're still going to see, when we cluster this data set with k-means, we will get a relatively high adjusted RAND score between our k-means cluster labels and our Gaussian labels. We're going to see something, we're going to see an adjusted RAND score of 0.8398. And so we're going to assume that, basically this is going to be our gold standard, if you will. We wouldn't necessarily expect to get a whole lot higher than this adjusted RAND score here. Now, because this is, the data set that we're actually trying to cluster here is only 50,000 observations, this is actually something that k-means can handle. K-means can definitely cluster a data set with 50,000 observations. And furthermore, it's definitely totally possible for you to load a CSV file with 50,000 observations into your Jupyter Notebook environment. But for now, we're actually going to assume, let's just assume that this is a really large data set in which, it's actually impossible for us to load the full data set at any one given time into your Jupyter Notebook environment. So let's actually now assume just this very unrealistic assumption that you can only load 5,000 rows of a data set into your Jupyter Notebook at any given time. So what we're going to have to do instead is basically figure out how to, or essentially what we're going to do is for this clustering technique 1 here, we're going to load our first batch into our Jupyter Notebook environment, cluster our first batch with k-means, extract the centroids, and then basically one at a time feed in the remaining batches and assign each of those observations to their closest centroid, okay? But we're going to do this in 2 ways. So we're going to do it in which the order of the batches has been randomized. In other words, you can basically assume that batch 1 is a random sample, or basically a representative sample of the full data set here. So that's going to be the first way we're going to run this algorithm. And the second way we're going to run this algorithm is in which each of your batches are now in a non-randomized order. Or in other words, each of your observations in batch 1 are simply just from your first Gaussian cluster. Each of your observations in batch 2 are from your first or your second Gaussian cluster, so on and so forth. So we're going to see if this ordering in which we basically run these 2 algorithms plays any bit of a difference in how this clustering technique 1 performs. And they're basically going to do the same thing with our Birch algorithm. So we're going to build 2 CF trees in which we're first building a tree where we're reading in the information one by one in this randomized order. We're going to cluster the observations using that CF tree. And then we're going to do it again in which we're reading in each of our observations into a new CF tree in which each of those observations are in a non-random order. And we're going to see essentially how much does that affect our clustering performance for these 2 algorithms here. Okay, so basically gone through all this here. So because this is sort of like a toy example and we're simply just testing the performance of this algorithm, we can in fact actually cluster the full data set. And so we do that a little bit later. But so let's use the random batch ordering for clustering technique 1 first. So we first read in our first randomly ordered batch here. Okay, so as we can see, these 5,000 observations look very similar to the 50,000 observations of our full data set. So this makes sense. Okay. And so we will cluster our data set into 8 clusters, simply just using k-means. Okay. We assign the cluster labels to each of those observations. Okay. And then we extract our centroids, our 8 centroids from that clustering. Okay. And so what you can do is you can use this function here, if you'd like, to basically read in each of your remaining batches into your Jupyter Notebook and assign each of those observations to their closest centroid. So we basically do that here. Okay. And so the nice thing is if we were to calculate the adjusted RAND score between the Gaussian labels that correspond to each of those observations in our full data set and each of the cluster labels assigned to each of those observations using this clustering technique here. When each of those observations were fed in a random order, then the cool thing is that that adjusted RAND score is 0.8385. Or in other words, for all intents and purposes, the best possible adjusted RAND score that we could expect to see when it comes to comparing the Gaussian labels to the cluster labels, or basically the best adjusted RAND score that we saw when clustering the full data set, i.e. 0.8398, is actually, we get an adjusted RAND score, which is very close to the cluster labels assigned to all our observations in the data set by using this technique. And the cool thing about this technique is we actually did not even need to cluster the full data set. We simply just clustered 1/10 of the data set and assigned the remaining observations to their closest centroids. However, it kind of makes sense that we would still get a pretty decent performance. So this is what we were expecting, right? Because these, the first random batch that we clustered and then we found the centroids for was fairly representative of the remaining data set, or the other 9 batches. Now, the thing here is if we were to basically do this same, or utilize this same technique again, take note, right? So like, this is now our first batch when the ordering of the observations in the batches is not random. So for instance, if we were to cluster this data set also, this initial data set also into 8 clusters, then we might expect that each of our 8 centroids are going to show up, where these observations are in the initial batch. So what that means is that when we read in all of these subsequent batches and assign them to their closest centroids, we can see that we're not going to get a very good clustering structure. So unfortunately, when we end up doing that, when our batches are fed in a non-random order, we ended up getting this adjusted RAND score between the Gaussian labels and the cluster, or the assigned cluster labels. We end up getting an adjusted RAND score, which is 0.439, so significantly worse. Okay? Okay. I think I've run out of time. So unfortunately, I'm going to add a little bit of extra content after class, basically just showing you how the Birch clustering algorithm works. But the bullet point is what we're going to see here is, good performance, not just with the random batches, but also for the non-random batches as well, which shows the superiority of the Birch clustering algorithm when it comes to, clustering observations in a data set iteratively. Okay. All right, I've gone way over, so I'm going to stop. All right, cool. So yeah, hopefully everybody has a nice weekend. I will record that video today at some point. I'll let you know when it's ready. And yeah, let me know if you have any questions. All right, thanks, guys.